Okay, let's go ahead and get started. Good morning, everyone, or good afternoon, and thank you for joining us today. My name is Kelly Timko, and I'm from Galarath. I will be your moderator for this live learning event. Thank you for taking time out of your busy schedules to learn something new. All attendees are on mute, so we can avoid any background noise. If you have any questions or you need any help, please use the chat function to speak with me. Welcome to Linear Regression, How to Make What's Old New Again, featuring Dr. Christian Smart and Sara Jardine. Dr. Smart and Ms. Jardine will be presenting this based on their paper of the same title, which was the winner of Best Paper in the Machine Learning track at ICEAA's 2022 workshop. So we're very excited to bring this to you today. Today's session is brought to you by Galarath, creator of the SEER cost optimization platform that helps organizations view, analyze, and optimize agile and traditional projects, cost, schedule, and risk scenarios, and their outcomes. You can find us on the web at galarath.com. Please stick around for the live Q&A period. It's going to be at the end, and this will be your opportunity to ask questions and make this directly relevant to you. We will also be providing a link in the chat window to a 2-minute post-event survey. And on Thursday of next week, we'll be giving away a $100 Amazon gift card from the pool of survey respondents. So be sure to take a moment and fill that out. If you're from a government agency and aren't able to accept a gift certificate, then we're also happy to donate that amount to a local charity if you're selected. If you know anyone else on your team or in your organization who you think should be joining us this morning, you can ask them to join us right now by sending them to galarath.com. Also, all the handouts from the session, a PDF version of today's PowerPoint deck, a video of the session when it's ready, and also a few other valuable handouts will be found at galarath.com. Our next virtual Lunch and Learn will be in August, and it will be announced by email. You can also follow at Galarath on social media channels for that announcement. Today's training is being recorded, and video will be available for later viewing on demand. We'll be able to provide the URL for those to you. All registrants will receive that. And please feel free to share that with any of your colleagues if you feel it would be of interest to them as well. Okay, today's presenters are Dr. Christian Smart, Chief Scientist of Galarath, and Sara Jardine, Senior Cost Analyst at Galarath. Dr. Smart has 20 years of experience with cost and schedule risk analysis, predictive analytics, probabilistic reliability analysis, and machine learning. His background in aerospace includes missile defense programs, nuclear thermal propulsion, hypersonics, and robotic and crewed space vehicles. And Ms. Jardine has over 17 years of financial management experience. She has served a broad variety of federal agencies, including the Army, Navy, OUSD, AT&L, DAU, Veterans Affairs, and Department of Homeland Security. She is skilled in cost analysis and course development, project management, requirements analysis, contract management, and budget management. So you're in very good hands today. Please hold your questions until the live Q&A session, and we'll make sure everyone's questions get answered. So with that, I'm going to go ahead and turn the presentation over to Ms. Jardine.
Thank you, Kelly. Let's just go right into the agenda. We're going to talk about different regression methods. One of the most traditional regression methods that most people are familiar with is linear regression. We will introduce other regression methods to include regularization and gradient descent and Bayesian methods. For regularization, you may not have heard of some of these regression methods to improve your results, but they include ridge regression, lasso, and elastic net. So let's go right into it. So why machine learning? Machine learning is gaining popularity as we enter an era where we want to try to collect more and more data. We want to create big data sets. And with big data sets, we want to analyze and create the best predictive models. Machine learning offers techniques to improve predictive accuracy. If it's not familiar, that linear regression, although be it is a very traditional method, is a machine learning method. There are also alternative machine learning methods that can improve your linear regression results, which we'll get into and demonstrate. Let's go over a recap of linear regression. It is a machine learning method, and it's a supervised machine learning method. It's very familiar to most people. It is linear in form, where the independent variables has a linear relationship to the dependent variable, which is the variable you're trying to predict. The input variables are normally distributed and not correlated with one another, and it takes the model form of y equals ax plus b, where b is the y-intercept and a is the slope and y is the dependent variable or the variable you're trying to predict. The most commonly used regression method for linear regression is ordinary least squares, and this is where a and b are chosen by minimizing the sum of squares of the residuals. And on the right-hand side, you'll see a plot of that linear regression, meaning a line that's straight between the independent variables and the dependent variables with the data points. And then that line represents the equation that predicts that data set. For our demonstration in this presentation, we're using a software sustainment data set. It was derived from multiple Department of Defense programs and represents software sustainment. When analyzing that data set, we determined that software changes and duration were both influential in estimating total hours, that being effort, which is the dependent variable. Since there's two variables, it's considered a multiple linear regression model. And that linear regression model is shown at the bottom with two coefficients and an intercept. Our software sustainment model and data set included 316 data points. So that's quite a bit of data points, would be considered a large data set. We partitioned that data set into two separate categories. We partitioned it into the training data set, which constituted 221 data points. It's roughly about 70% of the data. And then 95 data points represented the test data set. In machine learning, the reason why we partition the data set between training and test is because we want to use that test data set to determine how well your model predicts based on any new data that comes into your data set. So you want to make sure if you collect more data that your model is still stable. When you observe the plot on the left-hand side, this is a scatter plot. You'll see total hours on the left-hand side on the y-axis, and then as a function of software changes and duration. As you can see, when you look at the relationship of the line of the scatter plot, it's linear. However, something to make note of is that there's outliers in that data set. So in some of the regression models that we'll demonstrate later, we'll address how to address outliers in your plot. When evaluating different regression models, we look at goodness of fit metrics when running your regression equations. Goodness of fit metrics help you determine how statistically significant your model is. For our purposes, we use two different goodness of fit metrics. First being the R-squared adjusted, which measures how much variability in the total hours, which is the dependent variable that can be explained by software changes and duration, which are your independent variables. For the R-squared adjusted, the higher your R-squared adjusted, the better your equation is. That is the rule of thumb. The next metric we looked at was the root mean square error. This metric is the standard deviation of the residuals and measures how spread out the residuals are. And in this case, the lower your RMSE, the better your equation. So now when looking at our multiple linear regression model, we see that the R-squared adjusted between the training and the test data set is about 75%, so it's about the same. While the RMSE for the training was about 27,000 and 48,000 for the test, meaning the test data set actually got a little bit worse in terms of the RMSE. But looking at that regression equation, let's look at different regression methods to test to see if we can improve our linear regression model. One of the disadvantages of linear regression is that it's influenced by outliers, meaning it has a tendency to be biased and therefore is subject and at risk of overfitting. Two other regression methods to try to correct that is regularization and gradient descent. It can improve your models by optimizing your coefficients or your independent variable slopes and reducing the error. So let's take a look at, when testing those different regression models, how it may change our results. Let's talk about what regularization does. Regularization is an optimization method that balances bias and variance. It reduces overfitting of linear regression, and it also reduces error. It constrains the coefficients towards zero, and the goal of regularization is to create the most simple model and reduce overfitting. Regularization is an optimization problem, and it uses the loss function, as you can see, or shown on the slide, the equation for the loss function. It's also known as the shrinkage method. It constrains the slopes or the coefficients of your independent variables towards zero, and the optimization problem estimates those coefficients to generalize your equation so that any future data coming in can be introduced without changing your model so much. Let's talk about the bias and variance trade-off that regularization performs. A penalty is added to your equation and introduces a small amount of bias and therefore reduces variance. Bias has a tendency to over or underestimate relative to the mean. And variance measures dispersion around your actual value. On the right-hand side, as you can see, high variance results in overfitting, while high bias results in underfitting. The most optimal situation that we don't always get is that we want low variance and low bias, but that's not always realistic with some of our noisy data sets. Therefore, we have to try to find the balance between bias and variance to reach your most optimal solution and model to predict. For regularization, we're going to compare 3 different models and also explain what each one of these models, regression methods do, is adding a penalty term to constrain the slope parameters, which is regularization. The first one is ridge regression, next is lasso regression, and then elastic net regression. Ridge regression introduces a small amount of bias and then uses the loss function, as you can see, the formula shown on the slide, and adds a penalty to your equation. That penalty is represented by lambda, and the severity of that penalty is determined by its value of lambda. Lambda can range anywhere from 0 to positive infinity. Lambda is chosen such that through cross-validation, so it's varied until it optimizes your regression results. Those regression results that you'd be looking at for the most optimal solution would be your goodness of fit statistics. Next, with lasso regression, it's similar to ridge regression, but the value of lambda can actually shrink that slope to 0 versus just approach 0. In that case, lasso regression can also discard useless variables in your equation if they become meaningless or not statistically significant. Lasso regression represents a more simpler and easier to interpret model. Next is elastic net regression. Elastic net regression combines the properties of ridge and lasso regression, where 2 penalty terms are introduced into the loss function, those being lambda 1 and lambda 2. Also, through cross-validation, you would determine the values of lambda that produce the best regression goodness of fit statistics for your model equation. Elastic net shrinks the parameters of the correlated variables or even may drop them out of your equation. So that's regularization, those three methods. Next, let's talk about another optimization algorithm for regression, which is gradient descent. With this approach, you would actually use iterations to find the most optimal best fit line. The first step is the algorithm begins with fitting a random line to your training data set. Next, the parameters change little by little to make the best fit using the formulas to the right for the new intercept and the new slope. And then the goal is to minimize the sum of squares of error. And the line with the smallest error would be your best fit line. Looking at our regression results of the software sustainment data set, let's compare what the results were between the R-squared adjusted and the RMSE between the training and test data set. As you can see, for the training data set, the R-squared adjusted remained fairly the same, around 75%. The RMSE was about 27,000, but looking at the test data set, which determines how well the training data set predicts, it shows that linear regression stabilized at 75%, while the other regression equations went down, meaning that result got worse. So although we tried different regression methods to try to optimize our linear regression equation, in this particular instance, linear regression still prevailed as the best model. Sometimes that's not the case. Some of these machine learning methods could improve your results and should continue to be evaluated, but linear regression is still a very strong machine learning method that shouldn't be forgotten. Now I'll hand it over to Dr. Christian Smart to talk about what we learned in Bayesian methods.
All right, thanks everyone. Thanks, Sara. So what did we learn? We talked about regularization. What does it do? It adds a penalty term to constrain the slope parameters. Really, the results didn't really improve anything. So linear regression, just standard linear regression was the best method. So we'll go to the next slide. And we'll talk a little bit about Bayesian parametrics. So now for something completely different, as Monty Python used to say. Monty Python comedy troupe used to say, if you're old enough to remember that. When you have a small amount of data, which is often the case in aerospace and the Department of Defense, especially for specialized systems, there are only so many things you can do because the regression analysis that we typically do is designed for large data sets, typically 50 data points or more. So you need to come up with some other method. One, you can go out and collect more data, but that's a lot of work. You can use imputation to fill in the holes in your data. That's a little bit less work, but there's still some work to do. And also a little bit of guesswork. There's still some uncertainty in what those missing values are, even if you use the best methods. And then you could drill down to a lower level, component level. You may or may not have that data because then you may have more data available at that lower level. For example, missile defense may only have a handful of kill vehicles that they've developed for intercepting ballistic missiles. But if you drill down to the piece parts, like you start looking at inertial measurement units, you start looking at thrusters, there's lots of those. So you can build a bigger data set and build it up from a larger data set of data points. But Bayesian parametrics allows you to take the data you've got and then take all your experience and your other things. So it's kind of the easiest method in one way because it doesn't require you to go out and collect any more data. You've already got some experience. You may have a study that's been done on what this might cost in the past. That allows you to use this too. It allows you to combine all your data, including experience. It's relatively limited use in practice, and so I'm trying to promote the use of it and get more people to use it. It has a lot of potential because you don't really have to do a lot of extra work on collecting data, and that is the hard part. I had a meeting earlier today talking about, wow, we've got some data, but it's really messy, and 70-80% of your time is probably going to be spent, if you're really doing good work in analyzing the data, 78% of your time is going to be spent actually, getting the data in the right format to analyze. But this method allows you to start, doing some analysis on the data you've got right away without going out and collecting more data and then having to normalize that. So it's less work. The equation that's there, which is really probably one of the few equations in this paper or presentation, is this is the Bayesian theorem, Bayes' theorem, which relates conditional probabilities together. And Thomas Bayes was a minister in England, and he is the one who came up with this method first. And then Pierre Simon Laplace was a famous French mathematician who also did some work in this area. Next slide. So how small is too small? So we talked about if you have a data set and you're going to do linear regression, then you need 50 data points plus 10 data points for every additional independent variable that you want to add. So if you want 3 data points, 3 parameters in your equation, 3 independent variables, you're going to need 70 data points. So that's a lot of data. For some cases, we tend to have much fewer data points, and it's often the case. I mean, one of the ways in which people handle adding variables is you either start with the whole set of variables and you subtract them, or you start with the variable that's most closely correlated with your dependent variable, which, in this, for cost estimator, is cost. Could be something else, could be schedule, could be something else you're analyzing. But one way to do that is to start with the most closely correlated variable, you add that one, and then you look for the next ones, and you basically add variables as the fit improves. Studies have shown that about 30 to 70% of variables that are included in regression equations done in that manner are pure noise, and that's a matter of overfitting. And part of it is you're trying to include too many data points for the amount of data you have. And the basis for that rule of thumb that I've talked about, the 50 data points, is statisticians have done numerous studies on just taking random data, trying to fit a regression line, and then seeing what percent of the time they come up with a meaningful equation. Well, it looks like a meaningful equation just based on noisy data. Ideally, if it's just pure random noise, there would be no relationship between the two variables. But if you have a small data set, some pretty relatively high chance that you could get what looks like a meaningful regression equation. Okay, next slide. So here's an example. Consider the data set on the left. There's only 10 data points, but clearly we got a strong trend. It looks really nice, right? We got really high, got a nice R squared. If you're thinking about, X might be some sort of scope parameter like weight, and Y is cost. Say, okay, well, a coefficient of 0.6, that's kind of in line with my intuition. It looks pretty good. And R squared above 70% is pretty nice. That's only 10 data points, but clearly a strong trend. But these data, I generated these data at random using the random noise, using the random generator function in Excel. So this is purely random data. Okay, next slide. And here's another aspect to this. So if you have a small sample from a large underlying population, that small sample may not represent the underlying population. It's possible to find small samples that display a trend even when there's no relationship between the two variables in the whole entire population. So another example of being potential for being full blindness. If you only have the data points that with the X's on them, it looks like there's a pretty good trend between them. But if you had access to the full data set, you realize that there's no relationship. So you couldn't use X to predict Y. Next slide. Talked about Bayes' rule already. This dates back to the 18th century. So in the 1700s, Bayes wrote his paper, and actually I think it was published after his death. And then more recently, algorithms that were developed in the 1990s have made the technique more broadly useful. And this is a technique, and one of the things I like about this technique is when we work on government projects, if they succeed or they fail, they may not go out of business. They may take longer. They may steal resources from the programs, or they may get less done if they don't go out of business. Commercial companies that actually have a profit or loss, if they use a technique and it doesn't work well for them, they're likely to go out of business. Well, insurance companies have been using this technique for over a century for setting casualty insurance premiums, car insurance, that sort of thing, especially in settings where they have limited data, and it's worked for them because they haven't, they've stayed in business and they haven't gone bankrupt. It's also used in search and find. There's been some cases long ago when nuclear bombs were lost in the ocean, and they use searching. So use Bayesian methods to try to scope down where it could be, and then searching those areas and able to find them in many cases. It's using genetics testing, code breaking that dates back to the Enigma, which which helped shorten World War II. So it's been shown over and over again to work in practice. So I think it can work well for cost estimating as well. Okay, next slide. And schedule estimating if you're doing it parametrically. So we talked about Bayes' theorem. We talked about that. It's also used by hedge fund managers. So some of these hedge funds make a lot of money, and so it's been proven to work for them as well. It's been used in game theory. So it's not just an academic exercise using this. It's something that's been proven to work in practice. Okay, next slide. Okay, and then here's just an example. You have a mean deviation form for the equation y equals a plus b times x minus the average of the x values, and then plus your random error terms. This is a linear regression. We have a data processing data processing unit data set, which is basically the smarts in for the instruments and the payloads for spacecraft missions, robotic spacecraft. There's little data processing units, and in this case, I had somewhere between 10 and 15 data points, and I was able to fit this linear equation. This is one of the examples where you would apply linear regression, is because the data processing units, they have relatively limited ranges. And as Sara was talking about, one of the ways in which you would find that linear regression would be more applicable than another technique, even nonlinear regression, would be you have a limited amount of variation. So these things are small. They have a limited range for the power requirements in watts, and they have a limited range in cost. And these costs, around $1 million up to 10 million, maybe up to 10 million, typically less than that. So relatively small amounts of cost. So in this case, this is the equation I came up with, and so I applied that in practice to predict the cost of a spacecraft data processing unit. And then the CER estimate turned out to be 12.8 million. Now suppose that we had an analogy. It was a system that was bigger, but we thought it was it's bigger than it was cost more money, and they would think that it would, and it had higher power requirements. So could we use that? So we have an analogous mission that would give us some idea of what the potential intercept is if this were truly an accurate estimate. We have to adjust for that power and difference. And so that was around 24 million. And so once you adjust for that, your analogous mission adjusted for the power requirement was less than 12 million. So when you kind of basically Bayesian analysis takes a weighted average of the two based on your confidence in that. So combining those using our experience and our data gives us an estimate around 8.3 million. So a little bit different, right? A little different than what we were seeing with doing. If you did regularization or you did Lasso, that would just use the existing data that you had. If we have a little bit of extra data, we can combine that with our CER to improve the accuracy of our estimate, potentially improve the accuracy of our estimate. We think it should. Okay, and that allows us to do it in a rigorous improvement framework. It's not just, hey, it's about this, and it's not loosey-goosey. You're actually doing something with rigor and precision. Okay, next slide. And so, in conclusion, linear regression is still a powerful machine learning technique. It's oftentimes the best model. The characteristics of a linear data set included, like I mentioned, it's a limited range in either the dependent or independent variable, or typically both. You want less than an order of magnitude of variation. If everything's within the order of magnitude of variation, the relationship is likely to be linear. So you're thinking about, if you're trying to estimate a class of ships that are all kind of around the same size, give or take a few tons, or if you're trying to estimate cars. Another example of seeing this, talking to a cost estimator who works in France, has done some work for automotive industry. Cars don't have a huge range. Depending on what kind of cars you're looking at, the cars don't have a huge range in terms of their size. So, those kinds of applications. Talking about spacecraft, though, you have multiple orders of magnitude. So typically, depending on what you're looking at, if you're looking at the total spacecraft, you would see nonlinear relationships. But in some cases, like what I talked about with the data processing unit, where you have something that's very small, it's likely to be a linear relationship. The data processing unit is one example. If you were to go up to the spacecraft subsystem level and look at that, an example of that would be thermal control, especially the production costs for thermal control. It tends to be quite low. Not a lot of variation in that, typically not a lot of variation in the size of thermal control for robotic spacecraft. So those are a couple examples there. So you want that limited range. When you have a limited range, linear regression is likely to be your best model. Regardless of your data set, it's always good to visualize your data and see, look at the characteristics of your data before you start blindly applying methods to them. So take a look at your data, explore your data, visualize it, look at the correlation between the dependent variables, independent variables, explore the data and take a look at it, visualize it, create some charts and graphs and kind of see what makes the most sense. And you can also seek to improve your linear model by using regularization, gradient descent, and Bayesian methods. Okay, next slide. And basically, so thanks everyone for your time. And now it's time for Q&A. And we'll answer your questions now. And if you have, if you have any questions for us, reach out to us on LinkedIn. Sara and I are on LinkedIn, and also there's a number there you can call to talk to galarath.com directly.
All right, very good. Thank you, Dr. Smart, and thank you, Ms. Jardine, sorry. Before we dive into the live Q&A session, I want to let everybody know that we have dropped a link to the post-event survey in the chat, and a PDF version of today's presentation will be available at the end of that post-survey. So please take a moment to look at that. Also, you may submit all your questions using the Q&A button, and we will go ahead and open up the Q&A. So first question I have for you is, if you're using adjusted R-squared instead of R-squared, you should not have an overfit problem. Is that correct?
That's a great question. And unfortunately, the answer is no. You can use adjusted R-squared, and that will kind of account for the fact that you've got additional parameters, but that's just a really small part. That'll take it from, you may have something that's extremely overfit, and you may say, well, my R-squared is 75%, and well, because I'm using 5 variables instead of 3, my adjusted R-squared, it's going to go down some because it accounts for the number of parameters, but it doesn't make that big a difference. It's not going to take it from 75% to 34%. So it'll reduce it slightly, but it's not going to have a huge impact. Same thing for the standard error. The standard error will count for the number of parameters you have, but it's not going to make it go from 30% to 80%. It's not a really good indication. It is better to use adjusted R-squared, but just using adjusted R-squared is not going to keep you from overfitting. And when you're doing, looking at fitting, you should try to, the examples that Sara was providing earlier was, that was a data set that had hundreds of data points. And so we had a little bit of luxury to split the data out into a training set and then a testing set. So best practice helps you avoid overfitting. Most of the data is used for training, but then you assess the goodness of fit on the test data set. That you use a test data set to determine the coefficient. So that helps you prevent overfitting. Because if you have a really great fit on the training set and a really bad fit on the testing set, that indicates you're overfitting. Now, in other cases where you don't have as much data, we talked about this with Bayesian methods, you can do something called cross-validation that allows you to use all your data, but still do some out-of-sample testing. And that's a good way to go as well. If you have some questions about that, I'd be glad to talk about that offline. Okay, any other questions, Kelly?
Yes. Do you have any good all-in-one textbooks you could recommend that contain the topics that we presented today?
It's a good question. There are some good books on machine learning and regression analysis. I use I think it may be right here. Yep. So my favorite book on regression analysis, I've used it for 20 years, is Draper and Smith's Applied Regression Analysis. Now, it doesn't go into the cross-validation and the holdout kind of thing, but at least for the regression analysis, this is a good fundamental textbook. Or something that's more, you talk about the overfitting and that kind of thing. There's a paper that can be provided as a handout that talks about the overfitting and the cross-validation and that sort of thing. So I would refer you to that.
Okay, great. Thank you. What are some software tools to apply these regression models?
Well, you can do a lot in Excel. Excel has the data analysis add-in. It also has the linest function. So you can do a lot of data analysis in Excel. I don't think most of us are familiar with Excel and using Excel. Sometimes we overuse Excel, rely on it too much. But for doing the cross-validation, it would be better to use a tool like R or Python. There are packages out there that will help you with that and do it pretty quickly. The CARET package, C-A-R-E-T package in R, is good and will provide you with some ways to do cross-validation.
Christian, you want to go ahead and turn your camera back on? We're not seeing you.
Sorry.
Great, thank you. Another question. When are the other linear regression models proven to be more applicable than linear regression?
When are nonlinear proven to be more applicable than linear? Nonlinear regression is better, and this is one of the things you need to look at with your data. If you see patterns in the deviations of the actuals from the estimates, and there's a pattern as you look at the spread in the data, then you're not likely going to have a good. It's not going to be linear regression is not going to be a good method to use. That's something called a heteroscedasticity, which means different errors, and there's some sort of pattern there. You're doing something wrong. Linear regression, the error should be evenly over and under. And so if you're seeing a pattern, that's a sign that you're just using linear regression is not going to be good.
The other thing I wanted to add is if there are outliers in your data set that you don't want to throw out, you could consider some of those other regression methods to, reduce the bias, if those outliers are meaningful in your data set.
Thank you. Do you have any more? Go ahead, sorry.
I'll say that also with regularization, another thing people often use regularization for is it can help prevent overfitting because it will, some of the methods will force some of the coefficients to be zero. And so that will help you exclude some variables that, are kind of borderline statistically significant.
Okay, and what are the best times when Bayesian methods should be used?
When you have small data sets is a key one. I like Bayesian methods regardless. If you have different sources of information that you like to use, you have some expert opinion. So for example, you have some data, but you get something that doesn't quite seem right to you. So you have a fairly small data set, something that doesn't seem quite right. But you have some opinion about what the slope coefficient might be, or if a nonlinear equation, you have a power equation, y equals ax to the b. You might have some opinion about what the b may be, because the b value in that case tells you what some people call it economies of scale, but it's really more economies of size. What are the economies of size, which is typically going to be value less than 1. So if you do a regression analysis, unless it's software, if it's software, that value may be more than 1, but typically for hardware, it should be less than 1. So if you have a small data set and you get do a regression analysis that gives you a value greater than 1, but in your experience, you think that value should be something more like 0.6 or 0.7, you can take Bayesian methods into account, and that'll allow you to temper that strange-looking result with your experience.
Very good. All right, that wraps up the questions that came in. So I just want to thank everybody again for attending today, and thank you to our presenters. And please remember to click on the exit survey link in the chat so you can provide feedback on today's session. You can also have an opportunity to suggest topics for upcoming sessions, and also be able to download today's presentation and enter to win the $100 Amazon gift card. So please check out galarath.com to learn more about See Your Cost Optimization Platform. And remember that all of the deck and the other handouts are available at galarath.com. I will go ahead and keep the webinar window open for a minute so that you can have time to access that survey link. And thank you again for attending, and everybody have a great day. We'll see you next time.